Hello, my name is Joey Vagatis, a software engineer at Microsoft and the maintainer of the Patina component and platform configuration interfaces. In this video, I will be covering two topics: creating and configuring a Patina DXE Core crate for your platform, and creating, testing, and using a Patina component. This video was recorded using version 21 of Patina, and please keep in mind that I do expect you to have some basic knowledge of Rust and its developer tools. Jumping into the first topic, we will be creating and configuring a bare bones Patina DXE Core binary for our virtual x64 platform Q35. This will allow us to view a full boot to the UEFI shell once we are finished. In my VS Code workspace, we can see three open repositories. The first is Patina QEMU, a traditional EDK2 workspace that contains our Q35 platform. The second is Patina Firmware Patcher. This allows us to quickly patch in a DXE Core binary to an existing FV. And the third is our newly created Patina Q35 crate, which will contain our platform DXE Core binary. Taking a look at the Patina Q35 crate, I already have some basic scaffolding that allows us to compile the crate for a UEFI target. The main requirements was that we specified that this is no STD and no main, that we have a panic handler, and that we are exporting an EFI main function. So, running cargo build, we can see that this crate successfully compiles. Let's start by adding the two required crates to our cargo.toml file, specifically the dependencies section. The first is Patina, our SDK, and the second is Patina DXE Core, which, as the name suggests, is the DXE Core and all of its functionality. Moving back to our main.rs file, let's go ahead and define and configure the DXE Core. We'll start by defining a struct called Q35, and from there we need to implement three traits on this struct that allow us to configure different aspects of the Patina DXE Core. The first trait is the memory info trait. It holds platform configuration for memory management. At the time of this video, the only configuration is to prioritize 32-bit memory addresses when allocating. This is not applicable to our platform, which means we will be able to use the default trait implementation. The first thing that we will do is import all of the definitions that we need from Patina DXE Core, and then implement memory info on our defined Q35 struct. As mentioned, we do not care about overriding the default function implementations of this trait, so a simple no-op is all we need. Next is the CPU info trait. This holds platform configuration for CPU-related functionality. For ARM Architecture 64 systems, this includes the GIC base addresses. And for all systems, it provides a way to override the performance timer frequency. For most physical systems, this is not necessary. However, it is for the Q35 platform that we are building. So let's go ahead and implement the trait and set the override. For the override, we already have a full implementation here. We will not look at it as it is not important, but we will focus on doing the function override. So we'll start with implementing CPU info for Q35. And this does include a function called perf timer frequency, which optionally returns a U64. And this is a copy and paste that we have here. Again, this implementation and how this works is not important. It is specific to Q35. What is important is how we are overriding the perf timer frequency with a function implemented on this trait. Finally is the component info trait. This holds platform configuration for components. If you don't yet know what components are, they can conceptually be thought of as monolithically compiled EDK2 drivers. We will talk more in depth about components in the next section of this video, but for now, that should suffice. So let's go ahead and implement that trait also. For now, we do not have any configurations or components to register. So similar to the memory info trait, we will do an empty trait implementation. So implement component info for Q35. Now that we have implemented platform configuration for our 3 traits, it is time to implement the final trait. This trait is called the platform impl trait. Unlike the other traits, this one does not have any function overrides. Instead, we are specifying the implementation of memory info, of CPU info, and component info. For our case, we will be setting it equal to self, but this functionality exists so that platform maintainers can create generic implementations used across multiple platforms. So what this looks like for us is like this. As you've seen my IDE trying to tell us, there is a fourth and final type that we must specify, which is the extractor. This type is to specify the FFS extractor and the different types of compressed FFSs we need to be able to support. Patina does provide a couple of implementations, and these are defined in the Patina FFS extractors crate. For our use case, we will simply use the generic implementation, which is not that. It is the composite section extractor. So you can see that we have fully implemented platform info. With all configuration traits implemented for Q35, we can now define the static core and call its entry point in the start function of our EFI binary. We will start with defining the core. And instantiating it. Then we will move to the start function and call its entry point. And that is it. Now, when this binary is compiled, this function is executed, and we will automatically start the core. The only thing left to do is to add a couple of monolithic Patina components necessary for the platform to boot. Before we do that, let's move on to topic 2, which is how to create, test, and use a component. The component that we will be creating functionally does nothing important, but it will demonstrate some of the capabilities of the Patina component interface, specifically dependency injection. As mentioned in previous videos, Patina components are similar to PI drivers, but are monolithically compiled and use dependency injection in their function interfaces as an alternative to dependency expressions. Patina's dependency injection allows you to take a dependency on any type that implements a trait called param. Your component will not be dispatched until all dependencies are satisfied, and once dispatched, all dependencies are provided immediately through the component entry point. Patina provides some params out of the box, but developers are free to define their own param implementations. Let's explore some of the available param types provided by Patina. To review params provided by the Patina SDK, you should first navigate to crates.io, then to the Patina crate. From there, continue to the documentation and search for the param trait. You can see it is typically the first one. It is a trait. We select it. If you scroll to the bottom, you can see the implementers of the param trait. You can review the inline documentation and available methods for each of these types here. Additionally, the component module documentation contains a high-level overview of specific param implementations and their purposes. Let's navigate there by scrolling to the top of this page, clicking on Component, and scrolling down to the param types table. For our example component, we will be using the hob param to be provided a parsed GWTed hob from the hob list, and the service param, which is a way to consume functionality from other components. While not used in our example, the other notable params are config and config-mut. They allow configuration data to be shared across multiple. Navigating back to our workspace, you can find a newly bootstrapped component crate. Component crates must have the RFC-defined layout to ensure consistency across one another. Our crate has a component module, which will contain the component and its entry point. It has a hob module, which will contain the hob definition. And finally, it has a service module, which contains the service interface definition that our component will be producing. This interface will be usable by other components. Let's first navigate to the component module to view the minimum amount of code necessary to create a component. We simply define a struct that represents our component. It may or may not have state. We then implement the entry point function and tag it with the component attribute macro. As we write our component, we will add params to our entry point, which will be automatically injected during dispatch. The component we will be making in this example will produce a service that allows storing and retrieving raw bytes allocated with a memory type specified by a GWT. We will first start by navigating to the hob module, where we will define the structure that represents our GWTed hob. We will then implement the necessary traits for it to be treated as a hob parameter. Next, we will derive a few of the traits necessary for this structure to be treated as a hob param type. And finally, we will create a helper method to convert from a U32 to an EFI memory type. Let's now update our component interface to consume this hob. We will make it an option so that if a platform does not provide it, we will still provide the service using a default EFI memory type. Finally, we will update the entry point to override the default EFI memory type stored in core byte storage if the hob is present. Because we wrapped our hob param in an option, the dependency requirements for our component have not changed. However, if the hob is present, it will be provided. Let's move on to defining the service API definition. Our component will provide one implementation of the service. However, any component can theoretically provide their own. This allows platforms to override service implementations without affecting any component that relies on it. The service definition will be simple. It will contain three functions: one to store bytes, one to retrieve bytes, and one to remove bytes. One important thing to note about the service definition is that all three functions only take a reference to self. This is because all services require some type of interior mutability. This trait is public for two reasons. The first was already stated, in that we want to allow platforms to be able to override our provided implementation if necessary. The second reason, however, is that it must be public for other components to be able to consume this trait via their component entry point. Moving back to our component module, I've went ahead and created our own implementation of the service. To actually create the service implementation, all that was necessary was to define a new structure and implement the service API on that structure. From there, simply deriving the into service while specifying the actual service with this attribute macro was all that was necessary. Taking a closer look at our service implementation, I want to call out that we are taking a dependency on another service, the Memory Manager service. Let's update our component entry point to include it so that it is available when our component runs and we can use it to instantiate and install our service. With this change, our component will not run until the Memory Manager service is available. Let's move on to instantiating our own service. And finally, installing our service so that other components can use it. As you just saw, I added a param commands to our entry point. The param allows us to queue commands that apply structural changes to storage once the component execution has completed. You can see that we used it to add our service to the underlying storage. Now that our component is complete, let's register it with our Q35 Patina DXE Core crate, register a couple of other components, and then do a boot to UEFI. To register a component, we just override the component info traits components function and call add.component and instantiate your component. This is normally where you would add any private configuration if necessary during your instantiation. Our platform also expects the ACPI table protocol to be provided via Patina. Let's add the component that installs the Patina service and UEFI protocol for backwards compatibility. Finally, let's add a logger for our platform. Patina uses the log crate for its logging functionality. That means that you, as a platform owner, can use any log implementation that you prefer. For us, we will be using the Patina Advanced Logger, so let's go ahead and add that here. We start with the static logger, which logs to a UART 16550 IO port. We are using standard log message formatting. We are not filtering any modules. We are only logging at warn level or higher. From there, we need to initialize our logger and set that logger with the log crate. So let's go ahead and do that here. As you can see, we initialize by reading some data from the physical hob list, and then we set the logger with the log crate. And finally, our logger also comes with a component that provides a UEFI protocol that enables advanced file logging. So let's add that component. Let's jump back to Patina QEMU and boot with our newly created core. First, I want to talk about the build and run Rust binary script. It is a Python script that is maintained by the Patina team that utilizes the Patina firmware patcher to quickly build and patch the Patina DXE Core into an existing FV. This prevents the need of performing a full EDK2 build every time you want to make a change to the Patina DXE Core. This script supports many of the common developer workflows that we have found while developing Patina. Let's quickly look at the help of this script to see what all configuration there is. On top of being able to patch in a DXE Core binary, we actually allow you to patch in any binary. We allow you to specify the build target, debug and release, the platform that we're building for, so Q35 that we've been working with today, but also SBSA, which is also found in this repository. If you want to boot to an OS, we do support that with a simple command line, specifying both a serial port or a GDB port, most of the time for debugging purposes, but not necessarily in terms of the serial communication. Any types of features that you want to pass when compiling the Patina DXE Core. Let's go ahead and run the script to compile our new Q35 DXE Core, patch it into our already compiled Patina QEMU FV, and then run it. So you can see we're just calling the script and passing in the path to the local path to the repository that we should build. So right now we are building, we are done building, we are patching, we're done patching, and we're running. I did do a cut there just to save some time, not watching text scroll by while we booted, but you can see that we successfully made it to the shell. We started the startup niche and we reset just as we expected. So let's go ahead and take a look at the logs. I just want to show you some of the dispatching that we did. So we'll work from the bottom up on the components that the Patina components that we dispatched. So you can see here that we successfully dispatched the advanced logger component. This is pretty nice because it shows you the full component path of what we dispatched. And then in between these two dispatch statements are the logs that we had while executing this component. So you can see that it did its own logger message, I should say, but we did install the protocol interface. Same for the ACPI component. You can see the full path of what we executed, but you can see that it was a success and we did install some protocols. You can also see that we executed our core byte storage component. And there are a few other components that are automatically registered and executed by the core behind the scenes. So you can see that with the decompress protocol installer, system table checkstone installer, and CPU arch protocol installer. The last thing on the agenda is to talk about how to write on-system unit tests for Patina DXE Core. This is actually fairly simple. There is a crate called Patina Test, and it is a component crate that provides all of the definitions that you need to be able to quickly and easily write on-system unit tests. So we'll actually go through an example. I'm just going to copy and paste the test and talk about it. So we can see it here. You can see that this is a normal function with dependency injection and a result from a result type from Patina test. That is all an on-system unit test is. The only other thing that you have to do is tag that function with Patina test. This allows Patina test, the crate, to automatically gather all of the tests at compile time so that they can be executed at runtime. Because we do not support panic catching and panic unwrapping at this time, we do provide you special macro functions for asserts that instead of panicking, return this error on failure. By default, unit tests are not accumulated and not executed. To actually have the unit tests accumulated and executed, you need to register the component that is responsible for test execution. There is some configuration to the component, but we will not talk about that here. You can check the crates.io documentation for Patina test. Let's go ahead and compile and run the Q35 again, and we can see the test results. Off camera, I went ahead and built and ran Q35 with our new DXE Core. So let's go ahead and take a look at the log. We will start with the dispatch events, and we can see here that the test runner was successfully dispatched. So what that means is we should expect to see some Patina on system unit test logs in our log file. So we can search for that, Patina on system unit test results. So you can see that we actually have a lot of unit tests already built in. The Patina ACPI crate that we are using has a few unit tests. So does the advanced logger. And then the core itself has multiple stability and memory management unit tests. But here at the end, we can also see that our byte storage on system test was added and ran and passed. That is all the planned content that I have for this video. Today we talked about how to create and manage a Patina DXE Core binary and how to create and register a component. Hopefully you found these recordings helpful, and we should have more in the future. All right, thank you.